Thank you. Okay, so hi everyone. So this is See No Evil, Hear No Evil, hacking invisibly and silently with light and sound. So my name is Matt Wixey. I work for PwC UK on the ethical hacking team, and I lead the research function on that team. I run something called the Dark Art Lab, which is a research blog exploring kind of the more exotic aspects of information security. That's what I'm really interested in. I've been at PwC for about a year. Prior to that, I worked in a law enforcement agency in the UK, leading a technical research and development team. So I'm going to cover 4 areas in this talk. Part 1, I'm going to talk about different ways to jump air gaps using light and sound. Part 2, I'm going to cover surveillance and counter-surveillance. Part 3 is BANTs, which roughly translates to lulls, I guess. So it's kind of stuff I've found during the course of this research that doesn't necessarily have that many practical applications for security. It just amused me. As you'll see throughout this talk, that's quite a low bar, but hopefully you'll enjoy it as well. And then I'm just going to sum up and cover some ideas for future research in this area as well. So a few disclaimers: the views and opinions in this talk aren't necessarily those of PwC. As always with these kind of talks, all the content is for educational purposes only. This presentation doesn't cover vulnerabilities as such. So there's no kind of 0 days, there's no exploitation in many cases. It's about manipulating the inputs and outputs of a system in order to have a desired effect. And lastly, I'm absolutely not an electronics expert, so I've only been in the security field for about 5-6 years. Prior to that, my bachelor's degree was in English literature, which hasn't been particularly helpful. And I've only been looking at electronics for about the last year or so. You know, I kind of regularly burn myself with soldering irons, and I see magic smoke so much it's not even magical to me anymore. I just call it kind of regular smoke. So if you've heard of the Dunning-Kruger effect, this is where I am on the Dunning-Kruger curve, just to give you an idea. Okay, so on to the first video. So this is an example of something called Li-Fi, or light fidelity. And Li-Fi is data transmission through light. And I just wanted to show you this just to give you an idea of the kind of thing I'm going to be talking about. So this is adapted from a schematic I found on GitHub. I've made some modifications to it. There's a reference to the original, the repo at the end of the talk. But what I've got here is a phone with a headphone jack. But rather than come out to a pair of headphones, the data is going to come through to this breadboard of LEDs. This second circuit is a light sensor connected to a speaker. When I play the music, so what's actually happening there is that as the data is traveling through that cable, it makes the LEDs modulate, and then that modulation is picked up by that light sensor on the other circuit and outputted as audio. So you can also do the same thing with infrared LEDs. So this is exactly the same setup, but this time we're talking about invisible light rather than visible light. So that kind of concept of invisibly transmitting data got me interested in bypassing air gaps. So if you're not familiar with the term air gaps, it's basically when you completely isolate a computer from untrusted networks. So there will be a physical air gap between that computer and other computers and other networks. And there's been quite a lot of research on how to jump air gaps in various ways. Some caveats that go along with that research. There are 3 main ones. The first is that we assume that the attacker has already managed to put malware on an air-gapped machine, in order to attack it. So we're not particularly interested in how that malware gets onto the machine. That's not kind of the focus of the research. The focus of the research is on jumping the air gap. We also assume that the attacker has physical access to that infected machine, so they either work in the same office or they have influence over someone who works in that office. And lastly, we assume that the exfiltration that occurs from that air gap machine is quite slow, and it's therefore of quite small pieces of data. So we're talking about passwords, encryption keys, rather than kind of gigabytes of stuff. So an example of some of the research that's previously been done in jumping air gaps. I'm not going to go through all of these, but just to give you an idea, at the top you've got Van Eck freaking, which originated in the 70s by a Dutch researcher. And that was about the electromagnetic emanations from cathode ray tube monitors. So you could kind of sniff those and reproduce what someone was looking at on a monitor. And then you've got lots of work done by researchers at Ben Gurion University in Israel, looking at things like heat and various optical channels to jump air gaps. And this one down the bottom, Hassan and others in 2013. So they did a really good overview of some of the techniques that have been used previously. They also looked at ambient light sensors in mobile devices. And I'm going to come on to ambient light sensors in a bit. But the idea for an attacker, if you're attacking an air-gapped system, is you want to do two things. You want to be able to control malware that's on an air-gapped machine, which you can't do through normal channels because you have no internet access. And you want to be able to exfiltrate data, which you might not be able to do because of various protections on that device. So the first thing I'm going to talk about is jumping air gaps using light. Specifically controlling malware using ambient light sensors. So an ambient light sensor is a hardware component typically found in the frames of laptops and smartphones, but they're also in monitors and various other devices as well. And what they do is they vary their resistance according to the amount of light that hits them. And they're used for quite a benign purpose to kind of automatically adjust screen brightness, to kind of reduce eye strain, save battery life and things like that. But there is an API call in Windows that you can use to programmatically interact with the readings from that light sensor and from various other sensors as well. So my idea was, could an attacker create malware that reads those light intensity values from an ambient light sensor on a laptop through that API and then execute different commands according to the intensity and the sequence of the changes in light that hit the ALS? So a couple of problems associated with that approach is, firstly, we need to try and make it a covert activity because kind of shining a massive torch onto a laptop might kind of give the game away. And secondly, just controlling malware isn't enough. We need to be able to exfiltrate data as well. So the researchers I mentioned earlier, Hassan and others, what they did, or what their kind of proposed approach was that you would infect multiple smartphones with ambient light sensors, and you would then have to also compromise like a building management system in order to make the overhead lighting flicker on and off to control the malware. But I'm focusing purely on desktop operating systems. So this is a proof of concept of the malware. So you have the infected machine here that's visibly running the malware, and in the foreground here you have a really cheap laser pointer that's just been clamped into a table vise. And what you'll see is I activate the laser, it's going to kind of move across the surface of the ambient light sensor, and it's going to then execute a command on the laptop. So you can execute commands in this way without ever having to actually physically touch the laptop, let alone kind of issue commands over a network. Exfiltration is a bit more difficult. So again, this is using light to exfiltrate data. And in terms of optical channels for exfiltrating data from air-gapped networks, probably kind of the only approach that's been considered that's been viable from desktop computers is you read in a file and you encode it as like a QR code or something similar, and you flash up that QR code very briefly, kind of beyond the threshold of human perception. And the attacker would have a camera and they're filming the screen, and then they're able to go back and decode that QR code back into the original data. So I didn't want to kind of go down that approach. So my thought was, what the malware should do to exfiltrate a file is read in the file, convert it to binary data, to highs and lows, and then make very subtle changes in the screen brightness to simulate those ones and zeros. And then we'd have a hardware device to pick up those changes and then demodulate the data. So the first thing I tried was a really primitive kind of light sensor called a cadmium sulfide cell. You might have heard of those before. They're in really cheap night lights. It wasn't anywhere near sensitive enough. I then developed an Android app to do it using the onboard ALS on an Android device, and that wasn't sensitive enough either. So I ended up using this. So this is a light to frequency converter. These are fairly cheap, and these are so sensitive that they can pick up changes in the bioluminescence of bacteria as well as kind of register light changes through your hand and through flesh and that kind of thing. The kind of second challenge was in terms of actually making those changes to the screen brightness programmatically. The normal approach would be to use WMI. Obviously that requires admin privileges, so what I actually ended up using was two API calls called set device gamma ramp and get device gamma ramp. So what the malware does is it reads in a file, it registers the current gamma intensity level, saves it to a variable, and then depending on whether a bit is high or low, it will make a very small change in the gamma intensity level, which is then picked up by this device here, and it then sets the gamma intensity level back. So the idea is that it should be unnoticeable by the user. So to give you an example of this, this is the device. It's also got a micro SD module attached to actually write the data out. And what I'm going to do with the malware here is just do a test of this exfiltration. So I'm going to read in a file. You'll see the kind of ones and zeros, and then if you look closely, you should be able to see very subtle changes in the screen brightness happening. So there was one just there, I don't know if you caught that. And then from the attacker's point of view, what's being written to the SD card is data that looks like this. So if you've ever done any work on RF, kind of reversing, this is kind of amplitude shift keying, on-off keying essentially. So it's just kind of highs and lows that we can then demodulate back into data and steal it that way. So plonking a breadboard down next to a laptop isn't particularly covert either. So I came up with this. So this is a tie that's been kind of torn open down the back, and then you've got the same micro SD module, you've got an Adafruit Flora board which is designed for wearable technology, the same light to frequency converter that's connected with conductive thread, and the tie then folds back over the top of this. So the idea is, as a proof of concept, what an attacker could do is wear this tie and be able to exfiltrate sensitive data from air-gap systems covertly. Okay, so the next thing is Dreadphone. So Dreadphone is a tool I developed, again, as a proof of concept, which is command and control for air-gap systems using near ultrasonic sounds. So what do I mean by near ultrasonic? Well, the theoretical range of human hearing is 20 hertz to 20 kilohertz. So to give you some idea of scale, the lowest note on a grand piano is about 27 hertz, and the other end of the spectrum, bats communicate with each other at about 45 kilohertz. So human hearing between 20 hertz and 20 kilohertz. However, in practice, most adults can only hear up to about 16 or 17 kilohertz. Anything above that is inaudible to everyone but kind of adolescents and small children. So we call anything in that range 17 kilohertz to 20 kilohertz near ultrasonic. So whilst we can't hear it as adults, standard laptop sound cards are still perfectly capable of producing and hearing sounds at those frequencies. So there's been research done on this before and using near ultrasonic sounds as a command and control channel, so Tofsted and others in 2010 and Hansbach and Gertz in 2014. However, those researchers came across a problem when they were using standard laptop sound cards, and this is the problem. So this is a recording of near ultrasonic tones. So you shouldn't be able to hear the tones when I play them, but you will be able to hear something else which causes us a problem. So those clicks are generated from the sound card. And the reason, I think, is that it's due to electrical discharge from the sound card causing those clicks, which obviously makes it a lot less covert. But if I just play this through, what I can do is slow down the audio, and you'll be able to actually hear the ultrasonic or near ultrasonic tones themselves. So that was the actual near ultrasonic tone. So how do we get rid of those clicks? So what I did was I created 16 pre-generated wave files. Each wave file represents a near ultrasonic tone from 18.5 kilohertz up to 20 kilohertz. And for each of those wave files, applied multiple fade-ins and fade-outs and amplified it, and you end up with this lovely shape here. And this does not generate audible clicks, but the near ultrasonic tones still work. So here's an example of this attack working. So the idea behind this is both the attacker, who's on the left, and the victim, who's on the right, would have this malware installed. So they're both monitoring the input levels from the microphone. You'll note also my elite GUI skills. So the first thing the attacker is going to do is transmit a command by sending a sequence of those pre-generated WAV files. And then on the victim's machine, it reads in that, it interprets that sequence and then executes the corresponding command. And it's just the same in reverse for exfiltration. So I have a file on the victim's machine, just a small bit of text that I want to exfiltrate. So the attacker is now going to give the command to the victim to exfiltrate that file. And then if we stay with the attacker, what we'll be able to see here are the peaks that represent hex bytes coming back from the victim, i.e. the various kind of ultrasonic tones that are being played. When that's finished, we can then retrieve that sequence and decode it back into human readable text. So there is actually an interesting case study of this allegedly being used in the wild. Has anyone heard of bad BIOS? Bad BIOS, anyone? A couple of years ago, a few people? Okay, so the guy who founded the Pwn to Own competition, I forget his name, but he has posted a couple of blog articles about bad BIOS. It was malware that it obviously infected the BIOS of vulnerable machines. But allegedly what it also did was it communicated with other infected machines in the nearby area using near ultrasonic tones. So this one's been used in the wild. I'm not too sure about ambient light sensors. The final thing in the jumping air gap section is spectrogram. So spectrogram is purely an exfiltration or kind of steganography technique. It's not a command and control. The idea behind a spectrogram is exfiltrating images covertly. So Dreadphone is fine for kind of small bits of text, but what if you wanted to exfiltrate, a high-res image or something? So spectrogram is a tool I built that uses the same kind of technique that has been used previously in commercial music. It's not used very often. It's quite a rare technique. I've got two examples here. So what some musicians do is they embed images in audio, not in the audio files, so it's not kind of classic steganography, it's actually in the audio itself. And the way they do that is they will read in an image file, they'll iterate through that image and get pixel values, and then they will play certain frequencies for certain durations that correspond to that array of pixel values. When you then view that audio track as a spectrogram, which is a kind of visual representation of the frequencies in a piece of audio, you get a reconstruction of that original image. So you've got a face here and a cat on the right. So these are both examples from commercial music. So I built a tool that did the same thing. I'll try a live demo. So this is the tool. And let's say I've got an image that I want to exfiltrate. So in this case, it's just like a screenshot of a password. So what I do with my tool is read that in, specify a minimum and maximum frequency. So in this case, I'm sticking with mostly kind of near ultrasonic tones. If I hit generate, that writes me out a WAV file. Now, if I play this WAV file, can anyone hear that? Have interest? Yeah, okay, a few people, right. Now, if I view that audio track in a spectrogram, I can then recover that image. Now, whilst that was kind of a near ultrasonic, a few people still heard it. So what you can also do with spectrogram is you can merge that secret WAV file with a legitimate WAV file that plays audible audio. So I've got one here. Which is suitably dramatic. And then I can just merge this together. Okay, so this writes me out a file called merged. If I play that, you just hear the kind of the usual audio that you'd expect to hear. But again, if you view this in a spectrogram, you can still recover that image because it's at different frequencies and it's therefore still visible. And the idea is that you then cloak the near ultrasonic frequencies just in case there are people who can hear it. So in terms of mitigation for the kind of air gap bypasses that I've presented, Tempest standards are always worth a look. So there are kind of various ways to prevent data leakage and exfiltration. Removing or disabling ambient light sensors if they're not required. Screen filters do a really good job of muting brightness and intensity changes. And then for the ultrasonic stuff, you could be looking at white noise generators, ultrasonic detectors, or ultimately, if they're not required, disabling microphones and speakers altogether. Okay, so next section, surveillance and counter-surveillance. Who here has never heard of a laser microphone? Okay, a couple of people, that's cool. So I'll cover laser microphones and I'll cover various ways to compromise motion detectors as well. So a laser microphone is quite an old surveillance technique. It's used for kind of remote audio surveillance. So the idea is, let's say you're doing surveillance on a criminal group across the street and they're in a hotel room having a meeting and you're across the street in your office block or whatever, and you want to know what's going on in that hotel room. So let's say they've closed the curtains, so you can't film them, you can't lip read, and let's assume you don't have any assets in that room either. So you've got no informants, you've got no bugs or anything like that. So what you can do is shine a laser at the window. Now typically you wouldn't shine like a red laser, you'd use an infrared laser. Using a highly visible laser tends to give the game away somewhat. And the reason you do that is, as those people in that hotel room are talking, they're making air molecules vibrate. That makes the glass in the window vibrate. So as you shine the laser beam at that window, you then capture the reflection using a light sensor. The reflected laser beam will be vibrating also, or kind of shifting back and forth because of the vibrations in the glass. As that reflected laser beam moves across the surface of your light sensor, it causes changes in voltage, which can then be converted back to sound, and you can then hear what people are saying in that room. So it's typically two components. On the left here, I've got the kind of listener part of the laser microphone. So you've got the light sensor here. This is kind of adapted from an electronics kit that was intended to do something else. It's powered by 3 AA batteries, and the output goes to a standard 3.5 audio jack. So you can plug in speakers or headphones or whatever. And on the right, you've got, as you can see, a very sophisticated and expensive laser module that's powered by a 9-volt battery. So here's an example of this working. So I've got the listener, and the output is to a speaker in this case. The laser's switched on. And at the other end of the conference table, I have a phone that's playing music at a very low volume. Taped to the back of the speaker is a bit of reflective material to simulate a window. And at the moment, I'm blocking the reflected laser beam, but if I remove the obstruction, so that was quite a cheap laser microphone. So that cost about £30 to kind of build from scratch. But they are available commercially. They're typically only sold to like law enforcement agencies and various government agencies, and they cost kind of tens of thousands of pounds. The reason they cost so much is various reasons. You're looking at kind of the stability of the laser, audio processing, and that kind of thing. So they typically won't sell them to anyone else. But as you can see, if you can kind of achieve that with £30, then you could invest a little bit more money and you could have quite a viable product in order to be able to hear what people are saying. Okay, so moving on to infrared signals, sniffing, analyzing, and cloning. So cloning infrared signals is a very similar principle to RF signals, assuming you're talking about fixed codes. And it's essentially 3 parts. We need to be able to find a way to listen to an infrared signal, analyze it, and then replay it. If you're interested in infrared exploitation generally, there's a great talk by Major Malfunction, who's a British hacker. It's quite old. It was DEF CON in 2005, but it's on YouTube. Definitely worth watching. So if you want to sniff an infrared signal, the first way you could do it is just use a software-defined radio. So you could use a Realtek SDR. Because these are adapted from TV tuners, they still have an infrared component in them. So you can just use the RTL IR library, which is on GitHub, and that will give you raw pulse data from an infrared remote. You could use a dedicated infrared receiver and an Arduino device, so you could use the IR-lib library. And the nice thing about this is if it's a known consumer protocol, so like your TV remote, for instance, it will automatically decode the signal for you and just show you the decoded value rather than giving you ones and zeros. Or you could use a light sensor. So this is the same listener from the laser microphone. And I've got an infrared remote here. I'm just going to press this. And I'm recording the sound, and then that lets me visually inspect the signal, which is quite nice. And then playing it back, if it's a known protocol, you can just play it back. So in this case, it's NEC again, so I can just use the IR remote library to just play that back. If it's unknown, you have to do something similar to what you would do with RF. So you read the edges and the delays into an array, and then play that whole array back as well. So what's the point of talking about infrared signals? Why would we want to clone an infrared signal? Well, one example would be if you're trying to bypass some kind of security system that uses infrared remote controls. In this case, I'm going to be talking about an infrared motion detector. So there have been various bypasses proposed for infrared motion detectors. Porter and Smith in 2013 at Black Hat suggested various things. There was an episode of a popular television show where they bust myths. That covered kind of various ways to bypass infrared motion detectors. So here's an example of an infrared motion detector. So you have a remote here that has an arm and a disarm button. This grey circle here, this is the actual infrared detection sensor. So this detects changes in infrared radiation, i.e. Body heat, or heat generally. And this red bit here, this is the infrared receiver for this remote control. So the remote control is also infrared, which is a bit of a weird design choice, but that's how you arm and disarm the system. And then on the right here, this is just a device I created. That's an Arduino Nano, an infrared LED, and a transistor to drive it. And I'm just going to show you an example of kind of a classic clone and replay attack against this. So first thing I'll do is arm the system, just to show it's on. So it's working. If I then activate the Arduino, that just clones the disarm signal from that remote control and turns it off. Now, there's nothing kind of particularly interesting or innovative about this. It's just a normal clone and replay attack. And actually, from an attacker's perspective, let's say you wanted to do this, you've got two problems. So say this system is set up in an office environment, for instance, so it will probably be armed and disarmed once a day. So how do you as an attacker learn what that disarm signal is in the first place? Given it's infrared, you can't kind of sniff it from distance. You're either going to have to try and steal this remote at some point, or you're going to have to plant a device near the system in order to capture the signal when it's sent. Neither of which are kind of particularly preferable for an attacker. So the first problem, how do we learn the disarm signal in the first place? So I thought I'd kind of give a shot at trying to solve those problems. So I bought 9 of these devices. Now these are sold in the UK, US, Australia and various other places. They're quite popular. They are quite cheap as well. Each one you buy, you get the main system and you get a remote control as well. So I bought 9 of them and I sniffed the disarm signals from all of them. And the next slide should give you an indication of a potential security flaw in that approach. So any remote from any system you buy will disarm any system. And just to prove that, here are all 9 devices and all 9 remotes. So if I pick a remote up at random, it arms all of them. And if I pick up another remote at random, it disarms all of them. All right. It's probably the kind of easiest vulnerability I've ever found. These are cheap devices, I've got to say. So you kind of expect, well, you know, you buy cheap, you get cheap, but you'd expect at least a remote to be uniquely paired to a system. So that's the first problem taken care of, and it kind of negates the second problem as well. And the second problem is, how do you get close enough to the system to disarm it without setting it off? So I kind of had a stab at solving that problem as well. So here are two solutions for that. This is the first one. So this is drone to clone to pwn. So this is the same disarming circuit board that's just mounted on a drone, powered by that drone's internal USB port. The reason I've used a drone is that drones don't generate enough infrared radiation to trigger a motion detector until they've been in the air for about 45 seconds. So you've got the alarm in the foreground here. As you can see, I made a real effort dressing up for this video. So what I'm going to do is just power that board on the drone, and I'm going to fly it near the alarm. And if you listen, you should be able to hear the double beep of the alarm being disarmed. You can see it's still detecting me from this distance. Okay, so that was the kind of first way to get around that. This is the second way, so this is phone to clone to pwn. So has anyone here heard of a project called Digital Ding Dong Ditch by Sami Kamkar? Anyone? A couple of people? So Digital Ding Dong Ditch was a project Sami came up with. Essentially, he was using pretty much the same equipment here to be able to ring his friend's wireless doorbell from anywhere in the world. So this is kind of based on that. There's a couple of differences between this and Sami's project. So the first is this uses infrared. The second is Sami used interrupts and I'm using a loop. And the third is that this will delete text messages off this device. So what this device is, it's an Adafruit GSM module that has a SIM card in it. You have an infrared LED down the bottom, and then an Arduino here. This is checking every 5 seconds for new text messages. If it receives one, it opens it, and if that text message contains a certain string, it activates this infrared LED and disarms the alarm. So the idea is that you would hide this, or you'd pay someone to hide this near the system during the day when it's disarmed, and then after hours, once the system is armed, you can just send a text message from anywhere in the world to that SIM card and disarm the alarm remotely. So here's the alarm system as usual. What I'm going to do is arm it and just test it out to prove it's working. And then if we have a look at the sketch that's running on the Arduino, you can see it's checking for messages on that SIM card. Now in this case, the string that it's looking for on the SIM card is new phone, who dis. And once that's sent that phone number, within 5 seconds, it will open that text message and disarm that system. And then if we just have another look back at the sketch, you'll be able to see that it has opened the text message, it's contained the string, so it's sent the signal, and it's deleted the text message from the SIM card as well. And the last thing in this section is an active infrared motion detector. So this is a slightly different setup to a passive one. With an active infrared motion detector, you have two components, a transmitter and a receiver. And the transmitter is constantly sending kind of pulses of infrared light to the receiver. And if that kind of connection is broken by someone kind of walking across it, oops, then the alarm will sound. Now, if you constantly block the transmitter, the alarm continuously sounds. But what you can do is just create a device that mimics the signal coming from the transmitter. That's then accepted as legitimate, and then you can move in that area. So mitigations for these parts, so for laser microphones, there are various things you can do. You can deliberately induce vibrations on window surfaces. You can use things like wire screens and window coverings. You can detect infrared lasers because it's just infrared light at the end of the day. Laser mics are also subject to a lot of environmental interference, so things like double glazing, curved glass, also things like wind, rain and snow and fog and that kind of thing will really disrupt them. With alarms, ideally, you want to be using physical keypads to arm and disarm systems rather than remotes, because remotes can be sniffed. If you are using remotes, you want to go for ones which use encrypted rolling code algorithms that have been tested, that have been subject to some kind of security assessment, that use anti-jamming as well. And then you also want to use remotes paired uniquely to a device as well. That always helps. Okay, so part 3, BANTs. So the first thing I want to show you is this. So this is delayed auditory feedback. So this is a kind of psychological technique that's been around since the 1950s. And it kind of intersposes with things like neuroscience and biology and cognition as well. Delayed auditory feedback is when you introduce a latency between the sound of someone speaking and that person hearing themselves speak, because we expect that feedback to be pretty much instant. It was originally developed as a technique to increase the fluency of people with stutters, which it does. If you use it for, against people that don't have a stutter, it makes them less fluent. It makes them essentially unable to complete a sentence. It makes you kind of slur your words and elongate your sentences and stutter as well. So a couple of researchers in Japan built something called Speech Jammer a few years ago, which was a hardware version. I've built a software version, and I got some of my lovely colleagues at PwC to test this out. So what these guys are doing is they're wearing headphones, and they're reading a paragraph just from a website. As they're speaking, that sound is being recorded, and it's then being played back to them with about a 200 millisecond latency.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between speech and auditory perception.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between the speech and the auditory perception.
Delayed auditory feedback, also called delayed side tone, is a type of altered auditory feedback that consists of extending the time between speech and auditory perception.
And here's the voice in headphones a fraction of a second later. Some DF devices are hardware, DF computer software is also available. Most delays produce a noticeable effect of between 50 to 200 milliseconds. DAF usage with a 175 millisecond delay has been shown to induce mental stress. Surely this is stressful.
So the guy at the end there, his name's Zubin, he kind of leads our cybersecurity practice. Zubin said, this is stressful. And this technique has actually been shown to induce mental stress. So from an attacker's perspective, it's pretty unlikely, but one way this could be used would be if you're already on a network and you're seeking to disrupt an organization's activities or operations. If you were to wait for a really important conference call and then deploy this, you'd induce stress in people on that conference call and potentially influence the outcome. This does make people kind of quite frustrated and irritable. So it's one option, but it made me laugh, which is why it's in here. Okay, next thing, demotivating malware analysts. So this is based on a technique by Christopher Domas in 2015, who's a brilliant security researcher who's done all kinds of amazing things in x86 assembly. And he did a talk, I think it was BruCON, called Psychological Warfare in Reverse Engineering. And one of the things he came up with was working malware, which when viewed as a flow graph in the disassembler represents an image of his choosing. So in this case, it's a skull and crossbones. So this is actually a flow graph in the disassembler. And the kind of idea behind this is that the malware analyst would then be forced to look at this all day and kind of really wind them up. So I came up with a admittedly less sophisticated version of this using spectrogram. So let's say you're a malware analyst, and when you're running an executable, say in a debugger, but not kind of normally, if you run it in a debugger, you hear this sound. So you're going to be kind of quite curious, and you might try and extract whatever resource it is that's producing this sound. In this case, this is like a vanilla .NET assembly, so it's fairly easy to reverse and just pull this WAV file out of there. So you've got that WAV file, and it's driving you mad trying to think, what is it doing? Is it trying to exploit something? Is it some kind of covert communication channel? You know, what's the purpose behind it? And then eventually it occurs to you, or someone suggests, why don't you look at it as a spectrogram? And then you see something like this. Okay, Gilmore. So I think of everything I've ever done, I'm most proud of this. So to give you a bit of background on this, my wife is a huge Gilmore Girls fan. I don't know if we have any Gilmore Girls fans in the room. No, or no one wants to admit it anyway. So my wife watched all of this when it was first broadcast, and it was put on a popular streaming service a couple of years ago, all seasons. And she's watched season 1 through to 8 since then, about kind of 80 or 90 times. And during that time, initially it was just kind of passive indifference. So I was kind of like, well, this is okay. I can kind of see why people would like this. It's just not for me. And now I'm just kind of filled with loathing whenever it's on TV, and kind of active hatred, and I hate everything about it. So if I was in a mature marriage, we'd probably just talk about it, but I'm not. So I came up with Gilmore. So Gilmore is 2 parts. It's a Python script and it's an Arduino device. The Python script uses this awesome music recognition library that's available on GitHub called Deja Vu. Deja Vu fingerprints music, specifically MP3 files, using various techniques, fast Fourier transforms and things like that. And it stores those fingerprints in a database, and it then compares audio coming in to the songs in that database. So what my script here is doing is it's reading in 10 seconds from the microphone, every 10 seconds on a loop, and it's comparing that 10 seconds to the database. And one of the songs, in fact the only song in that database, is the Gilmore Girls theme tune. If there's a match above a certain confidence level, then it sends a byte down the serial port to the connected Arduino device. That Arduino device then clones the power off signal for my TV. So the upshot of all this is this. So I want to show you an example of this now. Because of kind of potential copyright issues, I've had to mute the video, but I'll release the kind of full version at some point. But you'll be able to see what's going on anyway. So this is the kind of pre-credit scene. So there's been no music yet. Okay, then the theme tune starts. TV turns off. Okay, so you could kind of apply that. You could apply that for kind of any theme music, or. So yeah, the kind of next step is voice recognition for this. So you can, anytime a member of the Kardashian family speaks, it turns off your TV. Okay, and the last thing I wanted to show you is Astrodrone. So Astrodrone is a technique to disrupt the ultrasonic altimeters in drones. So I'm demonstrating this with a Parrot. I'm not picking on Parrot specifically because lots of drones have these ultrasonic altimeters. I just happen to have a Parrot drone available. So drones use ultrasonic altimeters to find out how far away they are from the ground, kind of particularly when they're taking off and when they're landing. This is what it looks like on my model. So you have 2 parts. You have a transmitter and a receiver, and this works on the principle of echolocation. So this is something that's used a lot in autonomous vehicles and robots, as well as in nature. You know, bats and whales and dolphins and stuff use this as well. So what happens is you have a transmitter, and that transmitter will send out ultrasonic pulses at a particular frequency. Those sound waves will then hit an object and reflect back where they're captured by the receiver. And based on the width of the pulse that comes back, the receiver is able to infer how far away it is from that object or obstacle. So it's used in drones to kind of give greater stability when taking off and landing and that kind of thing. But what you can do as an attacker is you can send your own echolocation pulses aimed at the drone at the same frequency. And in the case of the drone, it will then think it's either at maximum or minimum altitude, and therefore needs to rise or fall immediately. So 8 times out of 10, it launches the drone upwards like a catapult into the ceiling. 2 times out of 10, 20% of the time, it will try and sink through the floor. And in both cases, it becomes unresponsive to commands. And eventually, if you're trying it in a room, like I did, rather than outside, because I didn't want to be that guy on the news, it will panic and it will just quit. So a similar technique was used by Liu and others in 2016, demonstrated at DEF CON against autonomous vehicles, Tesla cars. There's been lots of attacks against drones generally. But one of the things you can use to trigger this attack would be this. So this is a passive infrared animal repellent device. So you have a PIR sensor here. If this goes high, it sends out an ultrasonic pulse from this transducer. So here's an example of this. I'm just going to fly the drone over this device. And see if I try and get the drone to land, it just ignores the command completely. And then eventually what happens is it panics and falls down. And then you end up with a broken drone. So this is stage 2. So this is a colander, because at this time I kind of spent all my money on passive infrared motion detectors. So this has 4 passive infrared sensors. You've got 2 Arduino devices underneath the colander, and then you have 18 ultrasonic transducers arranged around here. So the idea is that the drone doesn't have to just fly directly over. It can be detected at multiple angles and brought down, or sent up, as the case may be. So in terms of practical applications for that, you could essentially use that as a kind of drone repellent to keep drones away from a particular area. We're doing further research on this at PwC, so we're testing it out with different drone models, different ways of emitting those ultrasonic tones and so on. Another thing you could use it for, if you wanted to, would be to keep drones away from you personally. Okay, so just to sum up then, so this is an overview of all the research, and as you can see from this, a lot of these elements are kind of connected in terms of the equipment that was used and the principle that was used behind it. So pros and cons for an attacker is that light and sound is great for physical engagements, that kind of thing. Difficult to detect and defend against, but leaves very little forensic trace as well. And as you've seen, as you've probably guessed from that talk, a lot of those prototypes are very cheap to design and develop. Cons is that obviously you usually need proximity to the systems you're attacking, they're subject to interference in various ways, and your kind of range and power very much depends on the resources that are available to you. So in terms of mitigations from a defender's perspective, the first step is knowing that these kind of techniques and attacks exist, and the feasibility of them and the kind of likelihood of them actually occurring is going to depend very much on the kind of organization that you work for and the kind of network and devices that you manage. But it's important to note that ideally you would block inputs and outputs to a system if they're not required, or at least ensure that they have a reliable failover. So in the drone's case, for instance, echolocation is not the only way to find out what your altitude is. There are other ways you can do it. Clone and replay attacks, very much still an issue. And there are a lot of limitations in some security products that use light and sound. So it's not sufficient, for instance, to just say, we have motion detectors, or we have cameras, or we have magnetic sensors, or whatever, because a lot of these will be vulnerable to some kind of attack, particularly at the kind of cheaper end, obviously. So future research that I'm going to be, that I'm hoping to look at, exfiltration via infrared, acoustic keylogging. So acoustic keylogging is when you infer what someone is typing based on the sound of them typing it, based on kind of fingerprinting individual keys on a keyboard. And then, as I said, various other work on the drone technique as well. So hopefully, in terms of how you feel about this presentation, you're on the left rather than the right. So music credits, all the music was kind of royalty-free or Creative Commons licensed, so the references are there if you want them. Here are the references I mentioned earlier, which will be on the PDF of the slides that they're going up on the BruCON website. So they're available there if you want them. And lastly, that's my email address and my Twitter handle if anybody wants to get in touch, got any questions, want to kind of collaborate on any research, or just to kind of give feedback on this talk, that'd be awesome. Yep, thank you very much.
Thank you.